Hey math friends, welcome back. This is AP Calculus section 3.5 day 2 notes. We're still talking about the chain rule because the chain rule appears in so many different types of differentiation problems. Yesterday we had an example where we had the chain rule combined with the product rule. Today we're going to begin our first example combining the chain rule with the quotient rule. So in example 1, letter A, our function is a quotient raised to a power. So if we begin the same way that we began yesterday, let's identify our inner function and our outer function. So for this particular problem, our outer function is going to be y equals something raised to the 5th power. And our inner function is going to be our quotient. So u is going to be equal to 2x minus 3 divided by x plus 1. So when I think about using the quotient rule with the chain rule is going to come into effect whenever I have to do the derivative of something. And remember, our quotient rule is low d high minus high d low over low squared. Our y prime, or our dy dx, however you want to say it, we have to begin with the chain rule first because our outer function is something raised to the 5th power. So y prime is going to be equal to, I am going to bring the 5 down, and then the inner function is my quotient, which is 2x minus 3 divided by x plus 1. And then the exponent on that is going to become a 4. But now the chain rule part says that I have to multiply by the derivative of the inner function. So here's where I have my quotient rule. So now I have to do low d high minus high d low over low squared. So begin with low. Low is x plus 1. D high is the derivative of 2x minus 3, which is 2, minus high, that's 2x minus 3. D low is the derivative of x plus 1, which is just 1. And this is all divided by low, which is x plus 1 squared. All right, and now I need to do some algebra. So the first thing that I'm going to do is in the top of my fraction here, I'm going to distribute and combine like terms. So I'm going to get 2x plus 2 here, and then 1 times 2x minus 3 doesn't change it, but when I distribute that negative, I get negative 2x and positive 3. So for this particular problem, these two x's cancel out. That doesn't always happen. So I really just end up with 2 plus 3, which is 5. So in the next step, I have y prime is equal to 5 times, I've got my 2x minus 3 over my x plus 1 to the 4th power. And now over here, I just have 5 over x plus 1 quantity squared. So I can do some more combining and simplifying. I can multiply these two 5's in the numerator together. 5 times 5 is 25. And then my quotient, 2x minus 3 over x plus 1 raised to the 4th power, I can separate the numerator and the denominator. So that's 2x minus 3 to the 4th power over x plus 1 to the 4th power. And then over here, since I multiplied those 5's together, now I have a 1 over my x plus 1 to the 2nd power. So the last thing that I could do, just to clean this up yet a little bit more, is to combine those families of x plus 1 in the denominator. So my final answer here is going to be y prime equals 25 times 2x minus 3 to the 4th power divided by the family x plus 1 to the 6th power. And this is the most simplified form of the answer. If this were a problem in your textbook, this would be the answer that they would give you in the back of the book. I really want to emphasize how important slow, careful algebra is when simplifying. The calculus is the easy part, and that's always done very quickly. It is the algebra that is the hard part and that is going to challenge you the most in these problems. Let's take a look at letter B. This one has some very challenging algebra when it comes to simplifying. Again, the calculus is not hard. It's going to be the algebra that is going to be hard here. So now notice that I have a quotient underneath my root, but I have a root. So we need to think about what is our outer function and what is our inner function. Remember that a cube root is a 1/3 power. So for this particular function, my outer function is going to be y equals something raised to the 1/3 power. And my inner function is going to be what that something is, which is my quotient, x squared plus 2 divided by x to the 4th plus 3x. So again, when we get to the point where we have to multiply by the derivative of the inner function, that is when we are going to have to use our quotient rule to differentiate that inner function. All right, so first step, y prime is equal to, we start by differentiating the outer function at the inner. So I bring down the 1/3, the inner function stays the same, x squared plus 2 upstairs, x to the 4th plus 3x downstairs. And then I have to subtract 1 from my exponent. 1/3 minus 1 is -2/3. We've seen that before. Now I have to multiply by the derivative of the inner function, so this is where I have to do my quotient rule. Low d high minus high d low over low squared. So low is x to the 4th plus 3x. Times d high, derivative of x squared plus 2 is 2x, minus high, that's x squared plus 2, times d low, derivative of x to the 4th plus 3x is 4x cubed, plus 3. And again, this is all over low, which is x to the 4th plus 3x squared. Whew. All right, calculus is done. Now it's time for a lot of slow, careful algebra when simplifying. Now, if I asked you to do a problem like this on a test, I might perhaps say that you can stop after the differentiation step and you do not need to simplify. However, we do need to practice this type of simplifying because on an AP exam, this may not be an answer option. So you do need to know what this would look like in simplified form. So let's begin with simplifying the quotient rule part of the problem. So we've got some distributive property to do right here. And then we have some foiling to do over here. So y prime is equal to, and this first part, I could certainly rewrite that with the quotient getting moved downstairs and the -2/3 exponent becoming positive. So this first part of the problem is going to become 1 over 3 times, and then 2/3 power, remember that's a cube root of that whole thing squared. So x squared plus 2 over x to the 4th plus 3x squared. Okay, so that takes care of the first part, and we are not going to do anything more with that. So that is just going to keep getting carried through to our answer. But we can certainly do more with the second part here. So let's start with distributive property. 2x times x to the 4th, that is going to be 2x to the 5th. And then 2x times 3x is going to be 6x squared. Next, I have to FOIL those two binomials and I have to distribute this negative sign to each term. So all 4 terms that I get from the FOILing are going to be negative because of that negative sign. So 4x cubed times x squared is going to give me negative 4x to the 5th. Then my outers, x squared times 3 is going to give me a negative 3x squared. Then my inners, 2 times 4x cubed is going to give me 8x cubed, so negative 8x cubed. And then finally my last, 2 times 3 is 6, times the negative 1 is negative 6. And this is all over x to the 4th plus 3x quantity squared. All right, so now let's combine our like terms in that numerator. And again, this first part here stays exactly as it is. So 3 times the cube root of my quotient squared. All right, so now in my numerator over here, when I combine like terms, 2x to the 5th minus 4x to the 5th is going to give me negative 2x to the 5th. I don't have any x to the 4th terms, so then my next term would be the negative 8x cubed. And then I have a 6x squared and a negative 3x squared, so positive 3x squared, and then my negative 6. And again, this is all over the x to the 4th plus 3x squared. And at this point, we stop because there really isn't anything more that we can do. We can't do any simplifying with what's upstairs and what's downstairs. If you wanted to rewrite this as one fraction instead of as 2 fractions, that's something that you could certainly do. I don't know if it looks any nicer, but you could put your 3, you could put your x to the 4th plus 3x quantity squared, and then your cube root of your quotient, x squared plus 2 over x to the 4th plus 3x quantity squared. You could put that all together on the bottom, and then your numerator would just be negative 2x to the 5th minus 8x cubed plus 3x squared minus 6. You could combine into one fraction, but really you have the exact same answer there. So to me, it doesn't really matter. They're both as simplified as they can be. The chain rule is also used when you have a composition of 3 or more functions, such as if we had y equals f of g of h of x, right? So if we have more than one function, we still use the chain rule. And just like PEMDAS, we start and we work our way. Well, with chain rule, you'd start on the outside and you work your way in, versus PEMDAS, we start on the inside and we work our way out. But it's the same idea. So if we're differentiating something that has a function within a function within a function within a function, we have to identify kind of what are all those different functions that are taking place in our problem. So example 2 is a great one. This is actually a composition of 4 functions. Because if I were to write this, this is y equals, and then my outermost function here is that something is being squared. So it's actually the cosine of the tangent of 3x. That whole thing is being squared. So as I said, this is a composition of 4 functions. All right, so what are those 4 functions? We'll just call them first, second, third, fourth, starting on the outside and working our way in. So our first function, or our outermost function, so I'm going to use some new letters here, is that something is being squared. So we'll say y is equal to w squared. So then our second function would be, well, what is w, right? Well, W is the cosine of something. So W is equal to the cosine of U. Okay, well, what is U then? Well, U is what's inside the cosine, which is the tangent of something. And we'll call that something theta. And so then finally, our fourth function is, well, then what is theta? Theta is 3 times x. So hopefully now you can see that we actually do have a composition of 4 different functions here. But we can still do the chain rule. It's not going to look very pretty, but we can do it. So our y prime, we are going to start with the outermost function and we're going to work our way in, just like we always do with the chain rule. So we start with, we're differentiating something squared. So you bring down the 2, and then everything else stays exactly the same inside. I'm actually going to make that a bracket. So 2 times the cosine of tangent of 3x. And again, if we brought down the 2, then our exponent becomes a 1. So I'm going to write it just for emphasis. Then we're going to multiply by the derivative of the next function, which is the derivative of cosine. The derivative of cosine is negative sine. So now we're multiplying by negative sine of what's inside. So negative sine of tangent of 3x. And now we're going to multiply by the derivative of what's inside, which is tangent of 3x. The derivative of tangent is secant squared. So times secant squared of 3x. And again, now we have to multiply by the derivative of what's inside. The derivative of 3x is 3. So we can certainly clean this up a little bit. Y prime is going to be equal to, we can take that 3 on the end and multiply it by the 2 at the beginning and make that a 6. And oh, you know what? We can also take that negative sign from our negative sign and let's make that a negative 6. So we'll have negative 6 cosine of tangent of 3x times sine of tangent of 3x times secant squared of 3x. And that is going to be the best that we can do in terms of our answer. Well, any set of notes wouldn't be complete without an equation to a tangent line problem. So now we get to use our new chain rule skills, and it looks like we've also got quotient rule with chain rule to find an equation of the tangent line to the curve y equals 2 over 1 plus e to the negative x at the point 0, 1. So we know with our tangent line problems that we always have that 3-step process, right? Step 1 is that we have to find our y prime. So in this case, we are going to use the quotient rule with the chain rule. All right, so in doing that, we know that y prime is going to be equal to, all right, well, in this case, we begin with the quotient rule because the outer function is the quotient. And the quotient rule is low d high minus high d low over low squared. So low is 1 plus e to the negative x. D high, derivative of 2 is 0. Minus high, d low. Here comes the chain rule part because the derivative of 1 plus e to the negative x includes chain rule. Derivative of 1 is 0. But the derivative of e to the negative x, that's e to the u, so e to the negative x, times the derivative of the u, which is negative x. The derivative of negative x is -1, okay? So maybe on your paper, call attention to the fact that the chain rule part was right here. That's where we had to use our chain rule. And then this is all divided by low squared, so 1 plus e to the negative x quantity squared. All right. Then our second step in the process is always to find our slope at our point. So find the slope at the point 0, 1 means that I have to find y prime of 0. That's going to be my slope. So when I plug 0 in, I get 1 plus e to the 0 times 0 minus 2 times 0 plus e to the negative x is just going to be e to the negative x, but that's going to be e to the 0 times -1, and this is all divided by 1 plus e to the 0 squared. Okay, well, what do I get when I do the math here? 0 times anything just cancels, right? And then I get e to the 0 is 1 times -2 is -2 times -1 is +2. So my numerator ends up being +2. And then in my denominator, e to the 0 is 1. So I end up with 1 plus 1 squared. 1 plus 1 is 2. So 2 squared is 4. I end up with 2/4, which is 1/2. So there was some good algebra there. Please be careful. My slope is 1/2. So now finally, my third step in the process is going to be writing that equation of the tangent line using point slope form. So I begin with y minus the y value of my ordered pair, which is 1, is equal to my slope, which is 1/2, times x minus the x value of my ordered pair, which is 0. And then when I solve for y, I get y equals 1/2 x plus 1 as the equation of my tangent line to the curve. And if you wanted to check your work, you could certainly graph the curve and graph the tangent line and make sure that the picture actually agrees that this equation of this tangent line is tangent to the curve at the given point. The last example, example 4, says that r of x is a composite of 3 different functions. R of x is equal to f of g of h of x. And then they give us a bunch of values. They say h of 1 is 2, g of 2 is 3, h prime of 1 is 4, g prime of 2 is 5, and f prime of 3 is 6. At this point, I have no idea what I'm supposed to do with all that. But my job is to find r prime of 1. So I know that means that I am supposed to find the derivative of r, and I'm supposed to evaluate it when x is 1. So let's start by writing out what r prime of x would be using the chain rule. So I'm going to start by writing out an expression for r prime. All right, so r prime of x, and I know it's going to be long because I've got a bunch of functions that are composed. So r prime of x is going to be equal to, and again with chain rule, we start on the outside and we work our way in. So r prime of x is going to be the derivative of the outermost at the inner. So it's going to be f prime of g of h of x times, now I have to multiply by the derivative of the next inner function, which would be g of x, so times g prime of at the inner, so g prime of h of x, times, and now I have to multiply by the derivative of the innermost function, so times h prime of x. So there's an expression for my r prime of x, but I know that I want to find it when x is 1. So r prime of 1 should be equal to f prime of g of h of 1 times g prime of h of 1 times h prime of 1. Okay, now I think I'm going to start using all of those values that they gave me above. First of all, I know that h of 1 is 2, and I know that h prime of 1 is 4. So let's start by doing those substitutions. H of 1 is 2, so right here, this becomes a 2. So now I've got g prime of 2, and this becomes a 2. So I have g of 2 in there. And then h prime of 1 right here is 4. So this is 4. All right, now I keep going. And the next thing I know that they tell me is that g of 2 is 3. So this is 3. So now I have f prime of 3 times. And they tell me that g prime of 2 is 5. I'm using all the colors of the rainbow today. G prime of 2 is 5. And then I have times 4. So then finally, last one. Let's see this one. F prime of 3 is 6. So this is 6. So I end up with 6 times 5 times 4. This should give me the value of r prime of 1. So r prime of 1, 6 times 5 is 30, times 4 is 120. So I was able to answer the question.